Hi everyone. In this video, we will be covering the Hardware Systems Application past paper for the year 2019. This paper corresponds to the academic year 2018-2019. Before we get started, let's pay attention to some of the instructions so that we'd understand the format of this paper and how we can approach answering these questions. For section A, there are 4 questions which are provided, and we only need to answer 3 of these 4 questions. Remember, these are the short answer questions, which will consist of definitions, short answers, and some code which we will need to write. Section B also contains two questions. In other words, there are 2 case studies or 2 design scenarios, and we will be required to choose one of them, and we are going to answer all of the questions in that section. For the coding section of the exam, we will be required to write code in VHDL using the Quartus 2 program, and all of the code pertaining or corresponding to this question should be uploaded in a zip file to the examination's course Moodle, I believe, or if not, on a flash drive, depending on the format of the exam. Note that students will be required to achieve an overall grade of 40% to achieve a pass grade. So without further ado, let's get started. One thing to note, despite the fact that we are required to answer 3 out of 4 questions in this section and 1 out of 2 in the other section, I will be covering the content for all of the questions in detail. So let's get started. So question 1 here says to design a 4-input multiplexer in VHDL. There are 3 parts to this first part of this question, part A. The first is to write the entity for the design. The second says to write down a possible architecture to achieve multiplexer functionality. And the third is to write a second possible architecture. So how we should approach this question is first look at it holistically. It's asking us for a 4-input multiplexer, and we are required to write an entity and 2 architectures. We know that for any VHDL design, we can have multiple architectures corresponding to one entity. It's important to note that the entity only describes the black box for the system, whereas the architecture describes its functionality under the hood. As far as the entity is concerned, it only knows the input and output ports. So let's try and recap on what exactly is a 4-input multiplexer. Now, I'm going to attempt to draw on this platform here, and hopefully this could replace the whiteboard to an extent. All right, so we know that a multiplexer is a device which has multiple inputs, kind of like this, and depending on the value of some select bits, we can select one of these inputs. Okay, so if this is a 4-input multiplexer with 4 inputs A, B, C, and D, probably some output Q, and some select bits. Depending on the values of these select bits, we can select one of these inputs. Now, what typically happens with multiplexers is if we have n select bits, we can handle up to a maximum of 2 to the power n inputs. Okay, so what this means is that for 4 inputs here, we will have 2 select bits. And this could look something like this. If we have 2 select bits, that means that we will have the possible permutations of 0, 0, 0, 1, 1, 0, and 1, 1. What that means is when select is equal to 0, 0, we can probably select input A and put that going to output Q. With select equal 0, 1, probably B will be going to Q. At select equal 1, 0, then C will be going to Q, or rather Q will be equal C, and when select is equal to 1, 1, Q is equal to D. Alright, so that's basically how the multiplexer works. So based on this little schematic that we drew here, what this is telling me is that there are 5 inputs to this multiplexer, A, B, C, and D, as well as a 2-bit select and 1 output Q. So we could think of this design in multiple ways. So I'm going to attempt to draw the schematic here so that we can think of what the entity will look like. We could either have 4 separate inputs, A, B, C, and D, together with some 2-bit select input and 1 output Q. Okay, or we could think of this as having a 4-bit input something looking like this, say I, and it's 4 bits, so it's 3 down to 0, with a select input, and we know that our select input is 2 bits, so I'm going to put that as a standard logic vector of 1 down to 0, with a single bit output Q. And what that means is that when select is 0, 0, Q is going to be assigned the value I3. Then, for some value of select, Q will be getting the value of I2, I1, I0, etc. Alright, so what this means in a case like this is we have this 4-bit input here, I, this 2-bit input here, select, but we only have a 1-bit output. The reason that Q is not a standard logic vector is because it is only going to hold the value of one of the bits of I at any given point in time. There's no restriction on us writing the multiplexer using this input vector as opposed to using 4 separate bit inputs. That is simply a matter of whatever you are more comfortable with. What is important, however, is that we have a multi-bit select corresponding to the number of inputs. Okay. Alternatively, we may even have 2 separate select bits. But either of these designs is fine for writing our entity. So given this, let's get started with writing the entity for this multiplexer. Now I'm going to attempt to write the entity using Jamboard here. If it is not legible, I will also include it in a Microsoft Word document or probably type it up in Quartus 2. Okay, so first things first, looking at the question, it says write down the entity for this design. For 4 marks, we are only required to write the entity of this design. Okay, so nothing is going to change from what we're used to. We don't need to declare the package like library, IEEE, etc. We are only going to write the entity. We're not going to write the architecture just yet. So the solution to this would look something like this. Entity, I'm going to call it 4 to 1 mux. Right? And it's important to note that we can't start the name of this entity with a number. We must start with some sort of text like the word 4. Okay, so entity 4 to 1 mux is, and now I'm going to declare my ports. So that's port, open brackets. And we can go with using something like single bits. A, B, C, D. So what that means is that I am now following this architecture here. Okay? All right. So my ports A, B, C, and D are of type std_logic. And the reason I'm answering the question like this, where we are writing it down by hand, is that we will be required in the exam to actually write this solution out and write out the code. So it's always good to get practice writing out the code. Now, given the current situation with COVID-19 and all those things, I don't know if we will be required to type the solutions or write the solutions and scan and upload them. However, it's just good to get practice writing it. Once we can write it, we could always type it out. Okay, so I have bits A, B, C, and D of type std underscore logic. Sorry, I forgot to declare these as inputs. So these are inputs of type std underscore logic. Don't forget your semicolons. All right, I'm going to have an output Q. It's going to be, again, of type std underscore logic. And I'm also going to have my select bits, which are also inputs, but these are a standard logic vector that is 2 bits in length. Because it is 2 bits in length, it is going to be declared of size 1 down to 0. Right? Now this is the last port that I'm declaring in this entity, which means I don't need a semicolon after this close brackets, but I do need some closing brackets corresponding to the overall opening brackets here. And after that final closing brackets is where I'm going to have my semicolon for declaring the port. Yeah. And now I'm going to end off the entity declaration by saying end entity, and I'm going to quote the name that I gave above, 4 to 1 mux, again with a semicolon at the end. And that basically takes care of the first part of this question, which is to write down the entity for the design. Again, the entity only tells us what the design or what the schematic is going to look like. We declared the entity corresponding to this diagram here. We could alternatively do this one. Actually, let's have a look at this one now. Okay, so another way to write this entity, all right, keep in mind we don't have to write both of them. I'm just showing you an alternative way to write the entity for this design, right? And this is the same as the design that we have here, and they are both going to be worth the same amount of marks. Okay, whichever design you choose is just a matter of which coding style you're more comfortable with. So again, I'm going to declare the entity 4 to 1, sorry, entity 4 to 1 mux is, and our ports are now going to be comprised of my input I, which is going to be of type standard underscore logic underscore vector, and of course, because this is now replacing the 4 separate inputs A, B, and C above, the vector size is now going to be 3 down to 0, where I3 is going to be something like A, I2 is going to be B, I1 is going to be C, and I0 is going to be D. Right, so I'm going to put my semicolon here. My output remains the same because it is still a single bit output. And and my select bits are also going to stay the same because they are still the same 2-bit input that's going to allow me to select either I3, I2, I1, or I0. Okay, so this is still going to be my standard logic vector. Of size 2 or width 2. Right? Then I'm going to close off the brackets for the overall port declaration, put my semicolon, and again end off my entity declaration. Okay, so this is now going to be end entity 4 to 1 mux. Okay, and that basically takes care of multiple ways we can write this entity. We can choose either of these, whichever we're more comfortable with, but it's important to note that there's no difference in performance or anything. They're still going to provide the same entity overall, and they're still going to be worth the same 4 marks at the end of the day. Okay, so part 2 of this question now asks us to write down a first possible architecture to achieve the multiplexer functionality. Now, to kind of refresh our memories on this, let's look at how we learned to write code for a multiplexer in lecture 9. This is lecture 9 on conditional statements and VHDL vectors. Okay, so we looked at 2 different ways, conditional statements to write code for multiplexers. It's important to remember that a multiplexer is a type of combinational logic, which means that it does not run on a clock. And because it does not run on a clock, that is going to dictate how we write this architecture, because we can't use a process, and because it's combinational VHDL, it's going to dictate the type of conditional statements that we have. Now, in combinational VHDL code, the types of conditional statements that we have available to us are the when-else statement and the with-select statement. So we can look at 2 different ways to write this architecture. Okay, one of the methods looks something like this, which is a very high-level way or a very high-level approach of writing the code for the architecture. It basically tells us to depending on the value of the select bits, whether it's 0, 0, 0, 1, 1, 0, or 1, 1, we are going to set the value of some signal called cell. Cell is declared as an integer signal here, and we are going to assign it the value of 0, 1, 2, or 3. We're also going to assign a default value of 4. Okay, and then we are going to look at how the value of cell changes with a conditional with select statement. We are going to say with cell select, and we're going to assign our output the value of A when cell is equal to 0, the value of B when cell is equal to 1, the value of C when cell is equal to 2, and the value of D when cell is equal to 3. Of course, we must have a default case to take care of when the value of cell does not adhere to any of these values. The other way we can write this is using the with select statement directly. All right, so depending on the value of our statement cell, when cell is 0, 0, we assign Z the output A. We assign output Z input A. When cell is equal to 0, 1, we assign it the value of B. When cell is equal to 1, 0, we assign it the value of C, and so on and so forth. The difference between these 2 approaches is mainly the fact that they abstract the selection logic here separately and the assignment logic separately, whereas in the second approach, we bundle that logic together. Okay, so each of these, being a more high-level approach, can be one way that we can write the code for this multiplexer. The second way, corresponding to part 3 of this question, will correspond to a more gate-level approach. All right, so we know that a 4 to 1 multiplexer looks something like this. Okay, I have my select bits S1 and S0. I have my inputs I0, I1, I2, and I3. And I can write the code to describe how these gates actually work to give me that multiplexer logic. So this would be the second way corresponding to part 3 of this question here. And each of these is worth 7 marks. All right, so let's look at how we can write code for the first part of this question. All right, so for the more abstract architecture, I'm going to name it's going to be a behavioral architecture. So that's how I'm going to declare the architecture. Okay, so I'm going to say architecture behavioral of 4 to 1 marks. And it's important to note that you need to quote the name of the entity that you declared in part 1 above. So whatever name you gave your entity in part 1, you need to specify that name here. Okay, so architecture behavioral of 4 to 1 marks is. All right, and I would like to bundle the logic together and say, depending on the value of select, I'm going to select either A, B, C, or D. Okay, so I'm not going to declare any additional signals or anything like that, so I'm just going to say begin, and I'm going to follow the logic in the second approach here, where I will bundle my selection and assignment logic all in one. Okay, so that's going to look something like this. With cell, and cell here of course corresponds to whatever I gave the name of my select bit in my entity. Okay, so with cell select, right, just making some reference to the actual code that we have in the slides there. So with cell select, let me just see what I named my output. My output was called Q, so I'm going to say Q is going to be assigned A when 0, 0. So let's take a look at the syntax of this with select statement here. The signal or the port value that I'm monitoring goes between with and select, and the permutations and combinations of its values are going to be specified after the when statement within the body of this with select statement here. So with cell select, when 0, 0, in other words, with this value being under observation, when its value is 0, 0, I'm going to do this operation here. In other words, I'm going to assign A to Q. All right, and I separate these assignment operations with commas. All right, and notice that I only need to specify my assignment operator once. The different options will be separated by commas. Okay, it's also important to note that in this particular example on the slides seen here, we are using separate lines for each of the conditions. However, we can write all of this logic on one line because it's just separated by commas. The only thing that denotes the end of this statement is this semicolon here. Okay, but for the sake of readability and visibility, we are going to use separate lines. So Q is equal to A when 0, 0, comma, B when 0, 1, and of course, because these are standard logic vector or multi-bit values, I have to use double quotes. Okay, C when 1, 0, D when 1, 1, And finally, I have to put a default case for this with select statement. So I'm going to say, I'm going to give it the value x, which is a special character for standard logic data type, which refers to undefined. So x when others. All right, then a semicolon to end this off here, and that takes care of the with select statement for my multiplexer. The last thing that I need to do here is just to end my architecture. Okay, so that's end. What did I call it? I called it behavioral. Alright, you can say end architecture behavioral, or you could just say end behavioral. It does not matter. But this is essentially what one of the architectures is going to look like, and this corresponds to the high level architecture. So this is now the answer for part 2. Okay? For part 3, we are going to write the code to describe the gate level solution for the multiplexer. Okay? So I'm going to do that on the left hand side of this here, on the right hand side of this, sorry, to give me some space. Sorry. You can see part 3 is going to look something like this. Okay, so now that I am describing how data flows through the logic gates, this is an example of the data flow style of architecture. Okay, so I'm going to name this particular architecture data flow. So my architecture data flow of what did I call it? I called it 4-to-1 mux. And of course, mux is just a short word for multiplexer. Okay, so my architecture data flow of 4-to-1 mux is. So one thing that I need to do here is, well, first of all, let's try and understand how this actually works. I have my inputs, select 0 and select 1. I'm passing them each through NOT gates. And what that means is that depending on the value of S0 and S1 at any point in time, the value of I0, I1, I2, or I3 is going to flow to my output, in this case, Y. Okay? So how this works is that when S0 and S1 are 0, 0, the inputs of this AND gate are going to be 0, 0. The inputs of this AND gate are going to be 0 and 1. The inputs of this AND gate are going to be 1 and 0. But the inputs of this final AND gate here are going to be 1 and 1. Why? When S0 and S1 are equal to 0 and 0, the values are passing through these NOT gates here and are input into the AND gates. Now for I0, whatever the value of I0 is, whether it's 0 or 1, for I0 to pass through this AND gate, or any of the AND gates, the select bits must be 1 and 1 in each case. So in other words, when S0 and S1 are 0 and 0, these inverter gates here are going to make them 1, 1 at the inputs here. With respect to this AND gate corresponding to I1, the inputs to this are not S1 and not S0. Okay, that's not S1 and S0. The inputs to this one are going to be not S0 and S1, and the inputs to this are going to be S1 and S0. What that means for us is that we need signals to hold the values of not S0, not S1, as well as the outputs of each of these AND gates here. Okay, so one way for us to write this is going to look something like this. So before I actually begin the architecture, I'm going to declare some signals here. Right, and I'm going to say I'm going to call this not underscore S0, not underscore S1, and I'm going to have outputs of each of these AND gates, and I'm going to call them, well, let's treat these as A, B, C, and D. I'm going to call these outputs here W, Y, I'm going to just call it M and O, and P. Okay, and these are all, of course, single bit values, so they are going to be declared of type standard underscore logic. All right, so now we can begin what the architecture is going to look like. So the first thing I want to do is ensure that I take care of this inversion operation here. Okay, so I'm going to say not S0 is assigned the value of, well, the actual keyword not and my actual bit S0. Sorry, that's cell 0. I call the port name cell, so this is going to be cell 0. Okay, and that is, of course, corresponding to the cell port that I have here. Likewise, not S1 is going to be the value of not select 1. Okay, so now depending on the values of cell 0, cell 1, not S0 and not S1, I am going to assign the outputs of these AND gates M, N, O, and P here. Okay, so let's just say in the case of this input here, the only time I'm going to allow I0 to transition to my output here is when S1 is 0 and S0 is 0. In other words, when not S0 is high and when not S1 is high. Okay, so I'm going to write that like this. M is going to be assigned the value not S0 and not S1 and let me see which one. For 0, 0, that corresponds to signal A, so I will put A here. What does that mean for us? The value of M here is equal to not S0, not S1, ANDed with whatever was that input. I0, I'm going to just call it A in this case, right? The reason I'm calling it A is because when S1 and S0, cell 1 and cell 0 are 0, 0, that means that not S0 is going to be high, not S1 is going to be high, and A is just going to retain its value. So if A is equal to 1, M is going to have the value of 1, ANDed with 1, ANDed with 1, which is equal to 1. If A is equal to 0, this is going to be 1, ANDed with 1, ANDed with 0, which is equal to 0, and the value of A is then translated to that output M there, which is just this intermediate stage here. Okay, and we're going to continue along that trend where B is going to be the value of when cell 1 is low and cell 0 is high. In other words, my intermediate signal N is equal to not S1 ANDed with cell 0 ANDed with B. Okay, my intermediate signal O is going to be assigned the value cell 1 and not S0 ANDed with C, and finally output P is going to be cell 1 ANDed with cell 0 ANDed with D. And finally, my output Q is going to be assigned, that's equivalent to Y here, passing through this OR gate. That's going to be assigned the value of M or N or O or P. And that takes care of this data flow architecture here, which I'm going to explain in some more detail to draw parallels between the two architectures. Okay, so let me just end architecture data flow. Okay, so let's see exactly what's happening here. Drawing parallels to the architecture on the left-hand side from part 2, we know that our output A is going to be transmitted to, our input A is going to be transmitted to our output Q when the value of cell is equal to 0, 0. Right? We agree that in this case here, when cell, which is our input port, when cell is equal to 0, 0, Q is equal to A. So what does that mean? If cell 1, sorry, that's this on the left here, cell 1 is 0 and cell 0 is 0, that implies that not S0 is going to be, I'm going to draw these in a different color here, not S0 is going to be high, not S1 is going to be high, which means that the value of M is going to be 1 ANDed with 1 ANDed with whatever A is. So going through this AND gate here, we have the values of 1, 1, A, which means that A is going to be translated to the output here. Why? Well, if A is equal to 1, M is going to be 1 ANDed with 1 ANDed with 1, which is going to give me a 1. And if A is 0, that's going to be 1 ANDed with 1 ANDed with 0, giving me a 0. In other words, whatever is the value of A gets translated to the output here. Okay? Likewise, in the case of 0, 1, I assign the output B, I assign my output Q to the input value of B. When cell 1 is equal to 0, okay, so if cell 1 is equal to 0, that's here, that implies that not S1 is equal to 1, which means that in this statement here, not S1 is equal to 1. And in this part on the architecture on the left, we see that our select bit cell 0 is equal to 1, which means that this is also equal to 1. And whatever is the value of B is going to get translated through this second AND gate here, because we're going to have a value of 1, 1, and B. And whatever is the value of B is going to get translated to my output N. Okay, and the same logic applies for signals O and P. And the reason we store these in these intermediate signals M, N, O, and P here is so that all of these signals are going to go through this OR gate after. So whichever one of them is high, and only one of them can be high at any point in time, that value is going to be translated or sent to my output. In the diagram here, it's shown as Y. In the case of my entity, my output was Q. Okay, which is why we use Q here as the final output. So that basically takes care of the two architectures for this entity. All right. So that's parts 2 and 3 of the exam question there. Right. Last thing to note is that for these two separate architectures, we can't write one with this method of using with select, and we can't use this other method as the second method of with select. What we have to do is write one high-level abstract design using either this method or this method, whichever one you're comfortable with. And for the other 7 marks here, we are going to have to write this gate level design here, which is our data flow architecture. All right? So that's it there for question 1, part A, which in total gave us 7 and 7 is 14 plus 4 is 18 marks. All right? Assuming that we understood this design, this is a nice, easy way for us to get some marks in this paper. Okay? All right, so let's look at part B of the question now. It says, as you have now designed 2 architectures for the same entity, if you were to instantiate this entity in another design, which of the 2 architectures would be used by default? If the default behavior is not desired, then how do you ensure that one of the architectures is used for your instantiation? Well, what happens in VHDL is if you have multiple architectures corresponding to an entity, the architecture that was compiled most recently is going to be the one that's associated with the entity by default. So what that means is that if we had these 2 architecture bodies corresponding to this one entity, either one of these, well, this entity is what we wrote the architecture for. So if we had any of these, both of these architectures, corresponding to that entity, whichever is the architecture that was listed second would be the one which was compiled more recently. And by default, that would be the one which is used. If we were to explicitly state the architecture that I would like to use, we can only do so when we are using the entity as a component in a larger design. What that means is that I have to declare this entity as a component, probably as part of some higher level design in a hierarchical standard, or probably as the case in a test bench. Okay, so if I were to do that, this is part B of the solution. Yeah. So if I were to do that, it would look something like this. I'd have to give, just as I would declare a component in an entity and then instantiate that component, I'd have to instantiate the component something like this. Box 1, assuming the component has been declared, right? I'm going to declare that of type 4 to 1 mux. Okay, and then I'm going to say use entity work dot 4 to 1 mux. What work is that when we compile this code, it's going to be packaged in our library that we are currently using, and we're going to call that by default. It's going to be called the work library. Okay, so 4 to 1 mux and in brackets I'm going to specify the name of the architecture. So if I wanted to use the data flow architecture, for example, I'd do so like this. Okay, so I can either declare it like this, or I can do all of this in one line where, let me just see if I could, okay, never mind. When I declare the entity like this, or when I declare the component rather, of whatever was the name of the component, 4 to 1 mux, in brackets right after the declaration of the component, I can specify the name of the architecture like this. Alright, so again, to answer this question here, which of the two architectures would be used by default? Well, the answer for that is the one which was compiled most recently. And to ensure either of the architectures is used for your instantiation, as long as we see the word instantiation here, that implies that we are talking about creating a component from this entity. So the solution to that is, when instantiating the component corresponding to the entity, you can specify the architecture to use using this syntax here, and you can list either one of these statements here. All right, and that takes care of question 1. Great, so now we can move on to question 2 of the paper. Now, question 2 does not have any VHDL. Well, it has some VHDL, but it's mostly one of those questions where you just give definitions and short answers. Okay. Now, this may work in favor for some of us who don't really like VHDL that much, but it's important to note that it's important to know the answers for all of these short answer questions. One of the problems with this, as we have discussed, is that a lot of these the theory for these questions are not presented in the lectures, because this is not given to us in SPCS as content that's on the syllabus from Greenwich. How they do it is that if they have in-class discussions that the lecturer elaborates on, these questions would be based on his in-class sessions. So you may notice that some of the theory in these questions would not have been even covered in our lectures, because we don't receive those things as actual physical notes. All right. Anyway, this question is based on generally on programmable logic technology, which corresponds to lecture 5 if you want to look into the slides. So let's look at the solutions to this question. All right, so what I'll do is, for this particular question, I'll actually be writing the solutions in a Word document, because I'm not going to actually write those out on the Jamboard here. Okay, all right, so let's get started. The first question here says to explain with a short example why everyone is a programmer, for 4 marks. This is one of those fluff questions which you could just get 4 marks by giving any answer, right? One of the reasons why anybody could be a programmer, one of the reasons why anyone can be a programmer is just because general everyday day-to-day tasks require us to follow some series of logical steps to achieve some goal or some outcome, and we probably have different conditionals that we take care of in everyday life. For example, if the rain is falling, let me carry an umbrella, something like that, right? So an example of a solution to this could be, let me see, it says explain with a short example why everyone is a programmer. Okay, so you all know I could be a little verbose and wordy, so I'm just going to write this in my own words. You, of course, write your solution in your own words. Okay, so the statement, everyone is a programmer, can be justified since day-to-day tasks in day-to-day tasks that humans perform are essentially structured as a series of steps, like an algorithm, to achieve some purpose or outcome. For many tasks, we need to think about the order or sequence in which we execute them, and if they can be done in parallel. For example, when we're cooking, we can do different things in parallel, right? Additionally, there may be conditions, example, if, else, whereby depending on the condition, and a number of loops, we take different actions, right? That's basically one thing that covers, that's basically the answer for that question. Pretty straightforward, not very content intensive or theory intensive, right? And that's just a nice 4 marks there. So the second part of this question says that part B, justify why the use of SRAM technology for reconfigurable devices is rather power consuming. So to answer this question, let's just take a look at what we learned about SRAM technology. So that is, right, that's here. So from the lecture slide, it says the SRAM programming technology uses SRAM cells to control pass gates. When a 1 is stored in the SRAM cell, the pass gate acts as a closed switch and can be used to make a connection between 2 segments of wire. So what the SRAM looks like is something like this. And you see that we have 2 back-to-back NOT gates here, which allow us to retain memory in each of these memory cells. Now how this SRAM cell works is that each of these inverted gates here, which acts as a form of memory, can only handle 1 bit at a time. Okay? It says here, when a 0 is stored, the switch is open and the transistors present a high resistance between the 2 wire segments. This technology is easily implemented, allows reprogrammability, etc., etc. Right, we see some of the disadvantages here is that it is volatile, needs to be configured at startup, and high power consumption. So the question asks us to justify why the use of SRAM technology for reconfigurable devices, that's like FPGA boards, is power consuming. And the reason why it's power consuming has to do with these NOT gates here. All right, so for another 4 marks, solution for this question is in SRAM technology, information is retained by the 2 NOT gates linked back to back. Both of these gates consume power to be able to retain information, and they only store 1 bit of information. When using SRAM technology in an FPGA, because we are required to retain many bits by active elements, and it says here It's volatile and needs to be configured at startup. And it says that they act as small truth tables or small LUTs. Alright, so we're saying so far, hence, using SRAM technology in an FPGA, when using SRAM technology in an FPGA or any other reconfigurable logic, because we are required to retain many bits, because active elements are required to maintain many bits, and there is a lot of configuration, example routing, LUTs, between many bits. Let me just restructure this answer a little bit. And there's a lot of configuration. The active elements, the active storage elements, that's the NOT gates or the inverters, consume a large amount of power purely for setting up and configuring the device. Alright, again, you see the style of these answers are not really what we have covered in class, and they go in depth into a lot of theory things which may not necessarily be covered in the slides. So I kind of advise against answering a question like this. We have looked at VHDL in depth, and there are a lot of questions to which we could apply VHDL concepts like entities, architectures, much like question 1 just now. So I kind of advise that we stick to those questions. Of course, the choice is up to you. If you feel more comfortable answering a question like this, by all means, please do so. All right, so looking at part C now. Some current FPGA platforms use hyperregisters. Explain what these registers are for and which disadvantage of the FPGA platform they aim to address. Again, unfortunately, hyperregisters are not covered in this lecture because they were not given to us as part of the syllabus in the lecture notes, which was sent down by Greenwich. Okay, so we may not really be able to answer one of these questions. Still going to give a solution here. Okay, so hyperregisters refer to the introduction registers along the routing path. That's of course in an FPGA board. These registers can be used or bypassed, but are effectively introduced to shorten the routing path and split it into shorter paths, which then work within the design as a pipeline section. Routing introduces a large delay in an FPGA, and this approach of hyperregisters addresses this challenge. All right. Again, just reiterating that we have never really covered any of this because we were never told to actually look at these questions. Okay. All right. Part D says it's split into 2 parts. Explain which programmable logic technology you would use for defense and space application. Again, that's not a very intuitive question. We've never really thought about anything like that. So answering a question like that is really just what you really understanding this lecture and the context in which we are going to deploy this technology. All right, so we have 3 types of programmable logic technologies here. We know that we have anti-fuse, SRAM, and floating gate, right? Previous question was based on SRAM technology. Now, for something like a defense or space application, the technology to which we will align ourselves is that of anti-fuse technology. So for a defense or space application, anti-fuse technology is preferred as it is most reliable in a context where you may find protons and electrons flying around. Again, not a heavily discussed solution in class, not very intuitive. And I don't really advise that we stick to these questions. Okay, we probably want to answer one of the more VHDL based questions. The other two approaches, SRAM and floating gate, could be affected by protons and electrons. Why? Because in space, of course, the atmosphere is different. We could have different things affecting how our programmable technology works. And if we remember floating gate and flash technology, which is essentially EEPROM, they are based on MOSFETs which charge and discharge the gate of the MOSFET in order to retain memory. All right, and likewise, SRAM uses these back-to-back inverters, as we just saw, which floating electrons could affect, because they could affect the charge on these lines with which we use to switch on our read, write, and data lines. Okay, so that is essentially the answer for this question here. The next one, name one disadvantage of the technology you selected for the above application. Well, that is, of course, just a disadvantage of floating gate technology. All right. Yeah, so moving on there now. This is more the question that we could focus on, and this is probably the only one that we could probably get marks in, okay? So it says to write the VHDL process that generates a self-repeating asynchronous pulse, low for 10 nanoseconds, high for 30 nanoseconds, as shown in figure QE. So we have we are asked to write code to generate a waveform that looks like this. And we know that we have written multiple VHDL processes to do something like this in test benches, okay? In test benches, when we write our clock processes and our reset processes to generate the waveforms which control our unit under test, we always generate self-repeating signals, and we can always use different wait statements to select how long we want to be low for, how long we want to be high for. Okay, so an answer to a question like this would look something like this. Okay, so this is question 2. What part is this? This is part E. Okay. Right, so the process would look something like this. Okay, of course, because we are going to be using wait statements, our process is not going to have a sensitivity list, so it's just going to be the keyword process with begin and end process keywords. Okay, so we want to write a process which is self-repeating. So assume we have some signal called maybe A or something like that. We can just say A is equal to 0. We are going to wait for 10 nanoseconds. Then we're going to say A is equal to 1. We are going to wait for, in this case, 30 nanoseconds. And that's it. How does this achieve this? Well, much like when we were writing clock processes in our test bench, we just set the time for the period to be low, we set the time for the signal to be high, and as long as I don't have a standalone wait statement, this process is going to be repeating over and over and over, because that's just how processes with wait statements work. Okay, and it is going to yield a signal, an asynchronous pulse that looks something like this: low for 10 seconds, high for 30 nanoseconds, then low for 10, high for 30, low for 10, high for 30, over and over and over, right? And that's just a process there for 4 marks. Okay, so now we can move on to question 3. Again, I know we didn't really cover this in much depth because these are just definitions that we kind of have to regurgitate, and a lot of the content for these questions are not in the notes because, as the lecturer from Greenwich has advised us, he sets these questions based on what he teaches on the whiteboard, which is not known to us. So I highly advise against answering these questions. Okay? All right, so let's look at question 3 now. Question 3 is another VHDL question, another 20 marks. And it deals with a segmented display, much like the 7-segment display, except now we have 16 segments. Now we all know how to write code for a 7-segment display after doing our projects, which required us to write a 7-segment decoder. We are just going to extrapolate that logic to now a 16-segment display. So the question tells us to write RTL VHDL that takes an integer value in, and what we're going to do is just underline some of these keywords here. Okay, so we're going to write RTL VHDL that takes an integer value, drives a 16-segment display to display the corresponding letter. What is meant by the corresponding letter? Let's see. Ensure that your design can deal with the first 13 letters of the alphabet, all displayed as capitals. See figure Q3 for the 16-segment display. State any assumptions made. So first of all, let's try and figure out what we are required to do here. Well, it's going to take in an integer value, which means we're going to take in something like 1, 2, 3, etc. And it's telling us that depending on the integer value that we take in, it is going to display a letter, a capital letter for the first 13 letters of the alphabet. In other words, when I accept the number 1, I'm going to display the letter A. When I take in the number 2, I'm going to display the letter B, etc. And what that is going to look is something like this. Well, for the letter A, let me see if I could just increase the size of this. For the letter A, that's just going to be displaying something like this. Right, just trying to right. The same will go for the letter B. B could be something like this. All right. The letter C could probably look something like this. Just get these out of the way here. Right, the letter D is probably going to be this here. And we need to figure out how we do that for letters A to N, because we're going to do A, B, C, D, E, F, G, H, I, J, K, L, and M up until the letter M, okay? Which is going to be using these crossway segments here. So what that means is that the first thing we need to do before even so the first thing we need, let's look at what the question is asking us to do. Well, it's asking us to write the entity for this design. It's going to be 4 marks. And we're going to write the architecture for this design for 10 marks. And that 10 marks there is an easy 10 marks once we understand exactly what we are designing for. Okay, we have 16 segments here: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, and P. And we need to determine which of these segments are being lit at any point in time. And much like how we have a 7-bit vector to determine the lighting sequence for a 7-segment display, that means that the output of this entity is going to be a 16-bit value. And depending on if a 1 or a 0 turns on one of these segments, we are going to light up that corresponding segment in this display. Talking about whether a 1 or a 0 turns on display, that conversation about common anode or common cathode displays is going to be one of the assumptions that we make here. Okay, so when writing the architecture for this design, the question tells us to state any assumptions made. Well, one of the assumptions will be something like, assume that logic level 1 turns on a segment. Okay, and from there, we will know exactly how to write the bit sequences for our architecture. So let's first figure out the entity for this thing. Well, it tells us that we are going to take in an integer value. Okay, so I'm just going to put question 3 here. We're going to take in an integer value. We know that display decoders are not sequential designs, so it is not going to be governed by a clock and a reset signal. So what that means is that we are just taking in some integer, right? And it says take in an integer value, so I'm going to call that int val. And because it is going to drive a 16-segment display, I need to have a 16-bit output coming out of this thing. So I'm going to call this display. It is going to be a 16-bit output. Of course, that'll be 15 down to 0. Okay. Next thing we need to do is, so that's basically going to be the entity of this display. It takes in some integer value. It spits out a standard logic vector value. Pretty straightforward. Okay. Once we write down that entity, that's just 4 marks. But the important part of this is now is to take on the architecture of this thing. To figure out what we're writing in the architecture, we know that we could use with select statement, we could use a case when statement. Probably we're going to go with a case when or a when else statement. We have to determine what are going to be the bit strings to give us those displays. So what we would need to do is to write out a quick truth table corresponding to the different segments here. Okay, so I'm going to take in the first 13 letters of the alphabet. So that's, I'm just going to write down that here. The integers that I'm taking in are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. And sorry, those correspond to my letters that I want to display: A, B, C, D, E, F, G, and it says that we have to display them as capital letters. So that's another important thing to take care of, to note there. Okay, so letters A to M. And now we have to determine for segments A to P which of these are going to be on and which of these are going to be off. So I'm going to write that now like this. And these letters here correspond not to the letters we want to display, but rather to the individual segments like A, B, C, D, E, etc. Okay? Right, so A, B, C, D. Right, and this is something that we'd have to do when we are actually writing out this design. We'd have to draw this truth table. Okay? If we don't feel comfortable drawing out the truth table, It's just good to keep track of some 16-bit long string to determine what segment goes where, which means that we may need to redraw this thing to see which segments are on at any point in time. So maybe for a capital A, you want to display it like this. Maybe for a capital A, you only want to display it like this and use half of this display here. Okay, so if we are displaying the letter capital A, let's think about what segments will be on. What, A, B, C, G, H, I, J, and N. Okay, and if I am writing a bit string, my 16-bit string is going to be bits A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, and P. And we assume that a 1 turns on a particular segment, and that means that segment A is high, segment B is high, segment C is high, segment D is low, E is low, F is low, G is high, H is high, H is high, segment I is high, segment J is high, K is low, L is low, segment M also low. We're assuming that a 1 turns on the segment, right? Segment N is high, and O and P are high. Of course, this bit string here was just me figuring out what the bit string is going to look like by looking at the segment here. You could alternatively fill out this truth table. It's up to you. It's not necessary. The important thing to note is that we need to figure out the bit strings for each of these values. Okay, so let me just redraw the entity here so we know exactly what we're looking at. We're taking in something called int_val, and we are spitting out display. All right, I'm just redrawing this so we do part 1 of this question, which is us writing code for the entity. Okay, all right, so let's get started. My entity is going to look something like this. Entity, I can call this I'll call it display driver. I'll call it display unit. Okay, entity display unit is, and my ports are going to be what? Well, taking in int_val here, so I'm going to declare this as a port first of all. Int_val is going to be an input of type integer, and one thing I can do is actually specify the range of this integer so that I don't input values 14, 15, etc. So we said here that the input integer value that we're taking in can deal with the first 13 letters of the alphabet. The first 13 letters are letters A to M. All right. In other words, the range of this integer is going to be 1 to 13. You could also put 0 to 12 as long as you're handling 13 different values. But I'm going to put 1 to 13 because it's more intuitive for us to start counting. Letter 1 is A, letter 2 is B, etc. Okay, and then our output, I'm going to call that display val. It is of type standard underscore logic underscore vector, right? Because what this vector is going to do is it's going to hold a 16-bit string like this, and each of these bits is going to correspond to one of these segments here, much like with a 7-segment display where we have that 7-bit string. Okay, so this is going to be a standard logic vector of width 15 down to 0. Oops. All right, and just gonna write the closing brackets for this port here because I kind of ran out of space there. And then I'm gonna say end entity display unit. Pretty straightforward. Nice little 4 marks there. Okay. All right. Next part now for 10 marks requires us to find these bit strings here. We just have to write it down. So for part B, let me start a new page for this one. For part B of this question, what we may want to do is take note of what this segment thing looks like and state some assumptions here first. So the first assumptions we're going to state are this. Just assume that a high voltage logic 1 turns on a segment. Okay. Then we are also going to assume that the display vector is in the order A to P. That is, what did we call it? We called it display val, okay, i.e. display val bit 15 represents segment A. Just write it out, corresponds to segment A. And display val 0 corresponds to segment P. Why is this important? Well, when I am declaring this vector here, display val, if I declare this using a down 2 statement, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. With down 2, that means that this is bit 15 and this is bit 16. With, if I were to use 0 to 15 to declare that, then that means that this is bit 0 and this is bit 15. And that will affect whether this is bit A or bit P, corresponding to either display val 15 or display val 0, or display val 0 to display val 15, depending on which of these statements I use to declare the vector here. All right, now because we're accustomed and we're pretty comfortable with using the down to statement, we are going to continue using display val 15 down to 0, which means that display val 15, our first bit, corresponds to segment A, and our last bit, display val 0, corresponds to segment P. And that will now allow us to write bit strings out looking something like this. Okay, so here I had a bit string to represent a potential value A. B could be something like segments A, B, G, H, I, P, and O lighting, and you can continue writing out those values there. So that's something that we would need to have in this solution here, some sort of table corresponding to my values like A, B, C, D, E, F, G, etc. And we have to write out the bit strings, for example, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0. All right, so the reason why we want to have these values is because whether we write it here or not, it is going to be in the architecture that we write. And that could get a little bulky for us, so you want to ensure that you have the correct values for these different segments, because the marks are actually allocated as such, where it's something like 1 mark per correct value, or I think it's like give 5 marks if all the values are correct, or something of the sort, right? So let's see how we could do this. Much like how we did code for the 7-segment display, where we used a case when statement, that is also how we can write the architecture for this display unit. All right, so let's try something like this. Architecture, RTL. The reason I'm putting RTL here is because it says write the RTL VHDL. Okay, and RTL is just kind of like behavioral, where we specify these bit strings, but at a higher level than the gate level design. Okay, so architecture RTL of, and I called my entity display unit on the previous page. Is, and let's start. Begin. So what I'm going to do is I'm going to write a process called displayProc to help me take care of these statements. But you may be asking, but this is not a sequential piece of code. Why are you writing a process? Well, the distinction is that a process can be used to write code for combinational logic or sequential logic. However, sequential logic can only be written using sequential code or a process. We can describe combinational logic using sequential processes, but we cannot describe sequential logic using combinational code like when, else, or with select. Okay, and the reason I'm writing a process here is because a case when statement is going to work nicely for this, and that's kind of like what we're accustomed with when we're writing the code for a 7-segment display. Okay, we're just going to extrapolate that logic. So this is my process, which is sensitive to changes in that signal, what did I call it? Int val. Okay, so whenever the value of int val changes, is going to wake up this process. Okay, so this is the begin keyword for our process itself. Let me just expand this so we'll see it a little better. So in the case where int val is, we're going to have the different values for int val here. So we know that we're taking care of the first 13 letters of the alphabet, so I could have something like when 1 we were using, right? And this, of course, corresponds to my letter A. I'm just going to add a comment there. You don't need to write that out. What was my output? My output was called display val. Okay, so when int val is equal to 1, my output display val is going to be assigned the bit string. Remember, that's our 16-bit value there now, right? And that is going to be this long value here. So that's going to be 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0. All right, now it's important that you all evaluate each of the bit patterns for this 16-bit string, because I mean, that's just how this question is, right? It's 10 marks. As long as we do this part, figuring out this stuff here, and we remember the fact that we have to write a case when statement inside of a process, that's pretty much an easy 10 marks if you ask me. Okay, so when 2, and this of course corresponds to the letter B, display val is going to be assigned the value 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1. All right, I actually just have these values here on another screen, so I'm not going to actually derive all of these. I think you all should know by now how to derive these values. Okay, we just look at the diagram here. We know that the different segments are A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. It's a little hard to see, but you could probably discern it still. And you just have to figure out, what does a B look like, what does a C look like, what does an E look like, F, what does an M look like, because you have these crossway segments here for like the letter M, the letter K, all those things. Right, so now for the value of C, my display val is going to be 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. Right, and it's important to note syntactically for the case when statement, we have semicolons at the end of each line. Right, just going to do a few of these. I'm not going to do all of them. It's important for you all to do all of them because that's what's required for the 10 marks, right? So you have to derive all of these 16-bit strings and just write them using this pattern here. What I do want to pay attention to, however, is after you take care of when 5, when 6, when 10, up until when 13 was it for the last letter of the alphabet? Well, after that 13th one corresponding to the letter M, I'm just going to write out this value here, where display val is equal to we need to have our default statement here. That's going to look something like this. When others, well, display val, we're going to turn off the display. And of course, because we said that 1 turns on the segment, for this default case, we're just going to have 16 zeros. Okay? And then we are going to end off our process, end off our architecture, and that will take care of this 10 marks here. Okay, a bit tedious, but I think given about 15 to 20 minutes, we could easily figure this out and write out the architecture there, right? So let's see what the last part of this question asks for 6 marks here. The entity provided in the previous question drives a single 16-segment display. That's just this here. Design the architecture that uses structural code to ensure that 3-letter words can be displayed. How would you think about this now? Well, it's kind of like when we're doing a 4-digit 7-segment display. We would write code for one of those 7-segment display decoders, and then if we want to display 4 different units, we would create a component from that entity and create 4 different instances, or in other words, we would instantiate it multiple times. In this case, we have this 16-segment display, which from part A and B above, we know can display 1 letter at a time. That's from A to M. If we want to be able to display 3-letter words, and one of these things displays 1 letter, then we now need 3 instances of this entity that was created above here. Okay? What that means is that we now need to create another VHDL construct or another code file, which is going to have some architecture which creates 3 components of the previous entity and instantiates those 3 components. Now we don't need to write the code for the entity, we only need to write code for the architecture of this new design. Okay, so that is going to look something like this. Let me just pull the question back up here. The entity provided drives a single 16-segment display. It's telling us to design the architecture, so we don't need to write code for the entity. Design the architecture that uses structural code. So the structural code is going to take into account a component that is named display unit. So it's going to declare a component first of all. So we're going to have an architecture looking something like this. So this is now part C. Okay. Architecture, structural. Just write struct of some new entity. We could call this entity 3-letter. Okay, we're assuming that the entity has been declared somewhere, right? Is. And now, before the begin keyword of our architecture, we need to declare the component here. And that component is going to be our display val unit that was defined in part A here. Okay, so we are going to have component display unit is, and of course we know that when we are declaring components in some larger design, we need to put the port names again, right? So we need to write over these port names here, and it's kind of like just like an entity declaration, except we replace the word entity with component. Okay, so component display unit is, I'm just going to write my ports are int val and display val, right? So port int val is my input of type integer, and we need to ensure that the names are the same as the entity. All right, display val is my 16-bit output, so that's my output of type standard logic vector. And it is of course 15 down to 0. Right, that's going to be the end of that port statement there. And component. Right, now that we've declared the component, we can actually begin the body of the architecture here now. All right, and all I'm going to do is create 3 instances of this component here. So We're going to say, remember, to create an instance of a component that you declare, you just give the instance a name. I'm going to call it something like letter1 with a colon, and you just rewrite the name here, right? And of course, you know we need to do our port mapping. Now, we don't know what the ports of this thing are, but we could safely assume that it is probably going to have 3 integer values, right? Let's probably call this first, second, and third. They're going to be integer values, and there are going to be 3 display outputs. So we could call this not seg, let's use a more intuitive name there. We'll just call it display 1, display 2, and display 3. All right. What that means is that for this overarching entity here, this is a large entity which has 3 display units inside of there, right? The integer input of display unit 1, which I'm calling in my entity here letter 1. Letter 1's input is probably going to be the input of first, and its output is going to go to display 1. The integer value sec is going to be mapped to the integer input of display unit 2, and the integer value third is going to be mapped to the int val input of 3, and the display val output of 2 is probably going to go to some 16-bit disp2, and the display val output of this third display unit here is going to go to the output called display 3 in the larger entity. And the reason I did that is just so we could get values to put for the port mapping here, because whenever we instantiate a component kind of like this, we need to do port mapping here. All right. So for our port mapping, we know that the output of the unit is called, sorry, the ports are called int val and display val. So I'm going to say int val and display val mapping on to display 1, right? Okay. You may notice that we are not using the, actually let me actually put the port map statement here, right? So this, assume we had a port map statement here. We use these mapping operators like this. We know that we use this to map the port of the thing that we are instantiating to the overarching port or signal of the larger entity. Okay? When we are doing this port map, we can do this in multiple ways. We can use this explicit way like we know here. Or, if I wanted to, assuming that I have the order correct here, in other words, int val is declared first, display val is declared first as the ports of the component, I can just state the signals in the larger entity that I'm mapping to in consecutive order. So I could just say display unit first, comma, disp1. And what this is going to do is the code now knows that display unit has as its first port in the port declaration the value int val. So it's going to take first some signal in this entity here and map that to the first position int val here. It's going to take display and map, because we listed second in this map function here in these brackets here, it's going to map that to the second port that was declared in the component declaration above. So that's just a shorthand way of doing a port map, which we will follow for the rest of this question. All right, so letter 2 now is my second instance of display unit. All right, and I'm going to map the signal second from here to the interval of letter 2's display unit. And I'm going to map the output display val of the second display unit to my second output disp2. All right. If you are more comfortable using the port map statement, because that's what we learned, you can do that as well. All right. And of course, the syntax to do that will just look like this: display unit port map interval mapping to third display val mapping to disp3. Okay, both of these equally acceptable, each of these methods equally acceptable. Okay, all right, and that takes care of part C of this question. Yeah, again, assuming that we comfortable with the VHDL stuff, this is a nice easy question because it's just basically a 7-segment display with more segments, right? So that brings us to the end of question 3. Okay, so let's move on now to question 4. Question 4 again is one of those definition and short answer questions. There is some code in there, but we're not required to actually write code for this. All right, okay. So let's see what question 4 asks us. Question 4, first of all, asks what is the importance of performing a feasibility study as part of product design and testing a design as early as possible during the design. These questions are both 2 marks each, and the content for this question can be found in lecture 6, designing and testing digital systems. So we know that when designing a system overall, it's split into 2 main parts: design and testing. We have different design methodologies, and there are different steps in the design process. 2 of these steps are performing a feasibility study and testing of the actual product that is being designed. Okay, so this question asks for the importance of each of those steps. So first of all, what is the importance of performing a feasibility study as part of a product design cycle? Well, reasons why we perform a feasibility study is to check the technical possibility, the affordability of the product, its compatibility with the organization, and of course with the client's requirements, see if there are any ethical issues, to ensure that the design that we aim to create could actually be created, the materials and technology available, could it be done within a reasonable time frame, in other words, to get the product to market. Is it feasible enough to get the product to market in a reasonable amount of time? All right. As for testing the system, the importance for testing the system, well, first of all, we should start testing as soon as we start our design and implementation. All right. So the step for testing, testing of parts of the design, prototypes, and manufactured products. So when we looked at testing, we said that testing the system is important because it requires a significant amount of time to do it properly. As testing goes, it takes up, as we see here, a large chunk of time with respect to with respect to design and production. And this graph here essentially tells us that the longer we wait to test a product, the more expensive it becomes, or the more impact it will have financially on a company when during design. Okay, so the best way to deal with testing is to start by taking it into account when you design the circuit. The main problem with testing is related to test time. A full or complete test in practice is impossible. Hence, one could limit themselves to functional testing where the most commonly used functions of the test are designed. So to answer this question for these 2 marks here, what is the importance of testing? Well, testing aims to identify any problems. The earlier these faults are detected, the cheaper it is to resolve them, because if we perform testing later down and we do not catch those errors in time, chances are we may have to go and redesign things and rework things way at the beginning of our design process, which could mess us up not only in terms of time, but also in terms of economic impact and financial impact on the project. Okay, so just to get some formal answers there, let me just write these in here for question 4. We have question 4, sorry, part A, part 1. Okay, so the importance of performing a feasibility study is to ensure that the design can be created, that the materials and technology are available, and that the product can be created within a reasonable time frame to get this product onto the market. It also allows us to gauge the financial possibility of achieving the design and explore any potential ethical issues. Okay, part 2 now of this question. Testing aims to identify any design problems and errors. Testing should be started as soon as implementation is started, i.e., as early as possible, so that we can pick up faults early on in the design, thus lessening the financial impact of an error or bug later down. The earlier faults are detected, the cheaper it is to resolve them. So it is highly important to start testing as soon as possible. Okay. All right. So next part of this question says Verilog is similar to 2 programming languages. Explain what these languages are and how they align with Verilog. Well, we never looked at Verilog in this course, but Verilog is just another hardware description language, much like VHDL, in that it allows us to synthesize hardware components using software. All right. However, the syntax of Verilog is not very much like VHDL. The syntax is more similar to something like C programming. So those of you who are familiar with Arduino programming would know what C looks like. So when it says that Verilog is similar to 2 programming languages, these 2 languages are the language C and VHDL. So the answer to this question would be something like this. Verilog is syntactically similar to the C programming language. However, it achieves hardware design and is therefore functionally similar to VHDL. That's it. 2 marks. Nothing too much there, right? So kind of a nice question for us once we know the theory behind it. Okay, so part C. A piece of VHDL code has a signal named reset. A bit further on in the code, one comes across a signal named reset in all caps. Do these refer to the same signal or a different signal? Now, we know that in VHDL, for example, if I have a piece of code like this, we typically stick to keeping the capital and common letters the same throughout, all right? However, if I declared this component here as display unit with a capital D, capital U, and the rest of letters as common, with signals, VHDL is not case sensitive. So if I had done this with display unit in all caps here, it would have still been referring to the same component here. It's not good programming practice. However, that signal signal reset there does refer to the same reset signal in this code. So the answer to this question would be VHDL is not case sensitive, therefore reset and reset refer to the same signal. However, it is poor design practice to use different casing. All right, again, 2 marks, pretty simple. Now the big part of this question is this, the 10 marks for this part here, for part D. Okay, so part D says, explain in full what the following code aims to achieve and how it achieves it. And we're given a little piece of VHDL code here, and we are asked to decipher this code. So we need to kind of go through this code step by step, right? Part 2 here says, compare the following code, that's this piece of code here, with the one in Q4 part D, part 1 above. Which of the two results in less hardware and why? So by reading this, if we can't figure out the code from here, what this does, we could just look at this and kind of figure out what this means, what this is doing here. All right. Part E says, well, we'll get to part E after. So let's look at parts 1 and 2 of part D. Okay. So it says, explain in detail what the following code aims to achieve and how it aims to achieve it. The code says binv is equal to B when sub equals 0, else not B. C is equal to A plus binv plus 0 and sub. So this may look like a little bit of gibberish to us, but let's kind of decipher exactly what this code is talking about here. Okay, so I'm going to cover different pieces of this code at a point in time. Okay, all right, so first of all, I'm going to cover this. I'm going to cover this. All right. So the first thing that we see here is binv is equal to B. So we have some signal B, we have some signal binv, and it's equal to B when? Well, when sub, some signal sub is equal to 0, B is given the value of binv, sorry, this signal binv is equal to B. Else, in other words, when sub is equal to 1, binv obtains the value of not B. So this is kind of like a little multiplexer that we have here. binv is equal to B when sub is equal to 0. binv is equal to not B, in other words, the inverted value of B when sub is equal to 1. And that's just what the first line is doing there for us. What does the second line do? Well, C is equal to A plus binv plus 0 and the sub. So let's take this in parts. What happens when binv is equal to B? Okay, well, for binv to be equal to B, let's look at the case of when sub is equal to 0. Well, when sub is equal to 0, binv is equal to b. So we could then say that C is assigned the value of A plus B when sub is equal to 0. And this is not actual VHDL code, we're just deciphering what this code does here. Okay? Alright. Now in the case of when sub is equal to 1, what happens? Well, binv is equal to not b. So this means now that C is equal to A plus not B plus some other thing here. Likewise, this thing is A plus B plus some other thing here. What is that some other thing? Well, we're seeing the ampersand symbol here. We may be tempted to think that that refers to logical AND. So you may be thinking this is 0 ANDed with sub. So if 0 is equal to, if sub is equal to 0, 0 and 0 is 0. Or if sub is equal to 1, 0 and 1 is 0. But that is not the case. This does not refer to a logical AND gate. The ampersand in VHDL concatenates bits or bit strings together. What that means is that if I have 0 and 0, that's just going to give me the bit string 0, 0. If I have 0 ANDed with 1, that's just going to give me a bit string of 0, 1. So what does that mean now? Well, that means that in this case here, if sub is equal to 0 and binv has the value of b, then the second line just evaluates to A plus B plus 0, 0, because this is the case where sub is equal to 0, so 0 concatenated with 0 with the ampersand yields 0, 0. Now, when sub is equal to 1, binv has the value of not b, and C is equal to A plus whatever is not b plus 0, 1. Alright? And what this evaluates to now is this circuit is simply doing addition and subtraction based on the value of this bit sub. This here, when sub is equal to 0, adds signals A plus B together. When sub is equal to 1, that gives me the value A minus B. How does it perform subtraction? Well, I invert the bits here, and I add 1, which corresponds to what? 2's complement subtraction. Right? Now we know that with 2's complement subtraction, if we have, right, just to recap what 2's complement subtraction is, and it's in one of the review lectures, but we'll just do it on a slide here. If I have values, if I want to say 9 minus 4, 9 is 1, 0, 0, 1. 4 is 0, 1, 0, 0, and I expect to get an answer of 5, 0, 1, 0, 1. To do this, the thing that I'm subtracting here, I want to invert the bits, add 1, 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, 1, 1. And then I want to add these two numbers together. That's 9 plus the 2's complement representation of negative 4. And when I add these two numbers together now, that's going to give me something looking like this. 1, 0, 0, 1 plus 1, 1, 0, 0. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. And we know that if the carry is 1, the answer is positive and in its true form. I believe that is in one of these recap lectures here, which means that it's important for us to, it's in the first lecture, it's important for us to look into these lectures and understand these things, all right? So essentially, all this piece of code is doing is it's creating for us an adder-subtractor circuit, which, depending on the value of sub, if sub is equal to 0, the circuit adds. If sub is equal to 1, the circuit subtracts. And it's doing the subtraction using 2's complement operation. So the solution to this, the question says to explain in full detail what the following code aims to achieve. So the code creates an adder and subtractor where the sub bit determines the operation. When sub equals 1, the circuit performs the operation C is equal to A minus B using 2's complement subtraction. The 2's complement operation is done by inverting the bits in the first line if sub is equal to 1 and adding the concatenated literal 0, 1 in the statement 0 and sub. Okay, so this is D part 1. Part 2 now, comparing the following code with the one in question 4, part D, part 1 above, which of the two results in less hardware? So if we weren't able to figure this out here for these 6 marks, then maybe when we come down here we can see, hey, this thing is just doing addition when sub is equal to 0, else it's doing subtraction, right? Then we may go back up and kind of decipher this code here. Okay, so so we understand that this is performing addition and subtraction. We understand that this is pretty explicit in that it tells us exactly how these bits and how the data is going to flow through here. This, however, while easier to understand, actually results in more hardware, because what happens here is that in this case we are creating one circuit with some gates. Here, when this code is synthesized, the code is going to create an adder circuit separately, it's going to create a subtractor circuit separately, and then it's going to use sub as a select bit and perform a multiplexer between these two circuits, and the output of that multiplexer will then flow into the value C. So, a high-level takeaway from this is the more abstract a code is, the more hardware it requires, because it leaves the process of synthesizing the hardware up to the compiler, and the compiler will try to do so as it sees fit. If we write more explicit code, while the code is more difficult to write, it reduces the synthesis overhead. All right, so both pieces of code perform addition and subtraction based on the value of sub. The second code snippet is much less efficient in terms of hardware because it requires the creation of an adder and a subtractor followed by a multiplexer. The first code snippet only needs one adder, and the subtraction is dealt with through inversion, which requires much less hardware. Just create. just fix these errors here. All right, and that is basically the answer for part D, part 2. Okay, just reading it again. Both pieces of code perform addition and subtraction based on the value of sub. The second code snippet is much less efficient in terms of hardware because it requires the creation of an adder and a subtractor followed by a multiplexer. The first code snippet only needs one adder, and the subtraction is dealt with through inversion, which requires much less hardware. All right, finally, part E asks us to provide one benefit of using the generic keyword over the use of open ports to provide entities with a vector size that can later be adjusted. So I believe we looked at the generic keyword during the teacher own topic assignments, but the main takeaway from this is that when we are declaring a port with a vector, we need to specify the size of the vector. If we use generic, the vector could later be resized with no consequence. In other words, the size of that vector is not set in stone. All right, so solution to this, sorry, this is not part E, this is part 2. Right, now we are going to part E. Okay, so when using open ports, we need to specify the size of the vector and stick to that during testing and simulation. With generic, we give a default value and can immediately simulate and test without the limits of the vector size, i.e. can easily be resized. Or adjusted. And that's just another 2 marks there. All right, which brings us to the end of question 4. It's a mix of VHDL and definitions. All right, and that then brings us to the end of section A. The next thing that we're going to look at is section B, which is the coding and design part of the exam.